When it came out, it was really impressive and I was blown away. I've been doing this for like 20 years. I was really blown away by it. It was popular and it was popular from anything I've seen before, but it wasn't as popular as it is in this moment. And so what changed that was Chat-GPT. What it made me realize is this AI is an alien intelligence.
Hey, Brad.
Hey, Chris, what's up? We just recorded one, and then the guy was mowing the lawn, so we had to start over.
Yeah, we're back again from our perspective, but not from yours, so welcome. Today we're just going to jump into it. We want to talk about the concept of emergence and, specifically like emergent abilities of artificial intelligence. But to just begin, Brad, could you talk us through what is emergence generally?
So when I think of emergence, I think of two things. The first being you get something out that you didn't put into it, and that something out only comes about because you have a lot of something. So for example, the idea of wetness emerges from two hydrogens and an oxygen together. So if you just have a single H2O molecule, you don't have this idea of wetness. It doesn't really make sense. You just see electrical interactions. But if you put a lot of water molecules together in aggregate, the confluence of these water molecules creates a new concept. A new concept emerges called wetness, that you know what I mean by that. So that's the first thing. The second thing that comes to mind when you talk of emergence is that small changes to some kind of quantitative parameter in a system makes huge changes to its qualitative behavior. So again, just going with the water analogy. So let's say we turn the quantitative parameter of temperature up, you would see the water start jiggling a little bit more. And then all of a sudden at 99.9 degrees Celsius, and then it turns to 100, then all of a sudden you have this big change that the water turns into a gas. And so those are the two things that come to my mind when we talk about emergence. And so if we apply this to AI, there's some really interesting things, both of these vectors that come out. And I will discuss that specifically, and then I think there's a general concept to this that applies to computation in general, and we can touch into that. So you want to jump into AI, or did you have any other path you wanted to go?
Yeah, we can do it. One thing I thought of when you were going through the water analogy was like, if the water lands in a hole in the ground, you get like a lake or a pond. But if the water lands like in a city, you get a flood. And so, I mean, I know that's not what you mean when you talk about like emergence necessarily, but I just wonder like about that. Does the emergence change based on like the environment beyond just the scale of it?
I think what you're talking about is called context. So context matters a lot in our lives, and you could say something that is really funny with your friends in that context, but maybe you said in a different context, it's very, very bad. Or if you have water in a swimming pool, it's really good. If you have water in a toilet paper factory, that's probably not good. So that's different. That's context, and that's also really important. And of course, emergence changes as a function of context.
Gotcha. Cool. I mean, yeah, let's jump into it. Like in the context of artificial intelligence, what is emergent? What are examples of this?
Yeah, so the quantitative parameter we varied in the water example was temperature, but the quantitative parameter you vary in neural networks is the number of parameters. And what that means is a neural network is just a bunch of multiplications and additions. We call it weights and biases. And the more of these multiplications and additions you add, the more parameters you have in this model. It's like akin to the number of neurons in your brain. And so I actually have a nice little diagram I can share real quick that shows a specific example of this. So I just saw this blog post, 137 emergent abilities of large language models, but I just wanted to show this graphic in the beginning because I think it's a good illustration of that, and we can link this article. I actually haven't read the whole thing. So what you see is on this horizontal axis, the x-axis, you see the number of parameters in a log scale. And so what happens, and then you look at the accuracy of the task. So there's modular arithmetic, IPA, transliteration, word unscript. So these are just tasks that you test these models with. And you can see that there's basically linear or sublinear change. And then all of a sudden at a certain amount of parameters, you just see it shoot off. similar to it's a phase transition like we talked about with water. And so one of these emergent things we see is with its ability to solve tasks. You're just like, okay, AI is dumb, it can't do anything. We change the number of parameters, doesn't kind of helps, but then you keep going, and to a certain degree, it just shoots off the charts. And so that's one thing we see, but we also see this happen across tasks. So you learn something good on a single task, and then all of a sudden you can do many, many different related tasks, which up until that point you could only solve this task. And even if you could solve this task good, at a certain point you don't necessarily improve so much on this task, but you improve on a broad range of tasks. And then the third category is just in kind of fundamental abilities. So for example, in GPT-2 or BERT, for example, you could do things like transfer learning, you could add inputs and outputs and do supervised learning. But all of a sudden with GPT-3 and GPT-4, you can do prompting. So all of a sudden you get this totally new way of communicating with the AI that is an emergent thing that we couldn't even think about earlier. And so now we could actually have a conversation with reinforcement learning with human feedback, but we can actually prompt this thing now. And so prompt engineering is this totally new field that emerged just by increasing the parameters. So there's this idea, well, let me pause there and see if you want to take
Yeah, no, I
direction.
mean, it's interesting. Like one thing it kind of made me think of is like so it's an increase in parameters. Like as you scale these things up, you get these new abilities. And like two thoughts I had is like, one, what are all those things? Like, is it purely more data? Is it increasing vector dimensions? Or are there multiple ways to kind of scale the model up and get these emergent behaviors? And then the other one is just a comment, like the idea that as it gets more of these emergent abilities, it can translate them to different functions or different activities. That seems very human to me almost, because I find that in life a lot. Like you learn one thing and it may on the surface appear irrelevant to another thing, but you find when you start doing it, oh yeah, like that thing I learned about X is helping me with Y now, even though you never intended for that to happen. My question was just around like, how do the models scale up? Like, it's purely, parameters. What do you mean by parameters? Can that be an increase in the vector dimensions? Can it just be raw like data? You just feed it more information? Is it multifaceted, this process?
Yeah, good question. So you need three things for this to work. If you scale just one of these, it doesn't work. So you need, this is kind of well known now, but just to say it again, is you need compute, you need big, fast, parallel computers. And so in 2012, when we had AlexNet, which kind of started all this craziness, GPUs came out, and Alex Krzyzewski, he had some code that could run neural networks on GPUs. And so they're like, hey, let's use that. And it just crushed everything. So compute is important. And then you need a lot of data. So if you have a lot of compute, but not a lot of data, well, it's like having a human locked in a room its whole life. And unfortunately, there's some examples of that, even in humans, and they can't speak, they can't do cognition, even though they have a big potential intelligence, which is your compute. So compute's your potential intelligence, data is actually making it practical. And then the third thing is algorithms that can take advantage of the compute. So if you have a really good algorithm but doesn't scale with the amount of compute, then it doesn't really help you a lot. It's too rigid. So it needs to learn from the data, take advantage of the compute. And the interesting thing is the transformer networks that we're using today with GPT-3, it's not much different than like Walter and Pitt's neurons in the perceptron. It's really not so different. It's very efficient to use, and so it unblocks the scaling. And I think there's also, I don't think it's a coincidence, because we could have had a kind of a counterfactual history where we had a lot of data but not a lot of compute, or we had a lot of, in reality they all came about at the same time, and I don't think it's a coincidence. I think when we had better compute, it became super cheap for everyone to have a computer, and then like we love our dogs and children, and so we took a bunch of pictures and wrote messages on Facebook, and we got a ton of data. And then based on all that, there was more research into algorithms, and it all just kind of came together. But actually, I think there was a lot of time that the algorithm was there and the data and compute had to catch up. So I guess if I was to rephrase it, actually the algorithm was there for 50 years, and then the data and compute kind of came together. And
it's almost like this inevitability, like it was all heading toward this point, but then there were lagging components that had to catch up for it to happen.
Yeah, exactly. And so to your point of exactly how they scale, I think we talked about another point that Moore's law, you had a doubling in transistors every 2 years, and that's this line here. So this is an exponential. This is a log graph. So this is a straight line on a logarithmic graph is an exponential. So you have an exponential increase in that doubles every 2 years on kind of these first era machine learning models. And then in this modern era, you just see this much steeper exponential, and you have this 3.4 month doubling. And so you just see the scale is immense. And so there's this idea of the scaling hypothesis that, so this is test loss. So it's, what that means is you have some task, and loss is kind of the opposite of accuracy. And so the smaller this is, it means kind of the less errors the model's making. And again, this is another log graph. And so each time this amount of compute goes up by a factor of tens, and then the data set size and parameters. And you could see an almost perfect correspondence to an increase in data set size, parameters, and compute.
Wow.
And yeah, and so far we don't see an end to this. And so the kind of naive, there's more we could go into, but the naive thing is, well, then why don't we just keep scaling until we hit a blocker somewhere? There's kind of no conceivable or I mean, even theoretical limit to this. And I think that's what people are doing. Some people are arguing that we're missing kind of some fundamental things. I actually happen to believe that we can keep scaling it. And what's interesting and what elucidates this belief I have is in some of the research that Stephen Wolfram has done in cellular automata. And so what he discovered with these cellular automata, it's just a grid of black and white cells, and there's a rule. So in this first one, you have white, black, white. So you look up the rule, where is it at? White, black, white. So then the cell underneath is black. So you put it black. And then this one's black, white, white. So black, white, white. So it's black here. So you just update these rules. And so there's very simple rules. Like what is here? 6, 8. There's 8 rules here. And so you would naively expect that if we had simple rules, we'd have simple patterns like this. Or like so you would get simple rules would create simple patterns. But what he found, again, this emergence is, and I think this rule 30 was his favorite one, is that you could get extremely complex behavior and even random behavior that you wouldn't expect from these simple rules. And from that, he came up with some principles. And one of those principles is the principle of computational equivalence. And so what the principle of computational equivalence states is that outside of some obviously trivial computation, that you actually have the maximally complex computation. So you would kind of think that if you had more compute, more whatever, better algorithms, that there'd be this gradient from like you have like the most simple compute to the most complex compute. But what this principle is stating, there's actually only 2 classes. There's trivial compute and maximally complex compute. And Alan Turing came to a similar idea, Turing completeness. And so what it makes me think, so that's the kind of theoretical observation. Practically, obviously, to run this compute just requires a lot of resources. And so if you can make it more efficient, even though it's maximally computationally powerful, to realize that you need a lot of compute. And so I think the breakthroughs won't be anything fundamental, but they'll just make it more efficient to do it so that we can get there sooner without having to run. But I think even with the simplest computer, we would get there, but we would just need, let's say, 1 trillion years or something. And so we want to not wait 1 trillion years. And so with better models like transformers, we can get there in years, like a single digit number of years. And yeah, so that's my opinion on that.
Yeah. I mean, it kind of makes me think of the idea of nature versus nurture, where you have this kind of fundamental almost nature out there. You know that it exists and that it's this compilation of all of these simpler parts, but your ability to nurture whatever it is that you're trying to grow, it's limited by, I guess, our abilities or our understanding of how to really maximize the potential, as you put it. Does that seem apt?
Yeah, I think the nature versus nurture thing is a really good analogy to this kind of compute, algorithm, data. and even context. And so I think the data's the nurture piece, the compute is the nature piece, and the algorithm is kind of the practical piece which ties these together and makes better use of the compute, makes better use of the data, and is the glue which makes these run, like the operating system on the hardware.
We're becoming better parent for our data.
Yeah, exactly.
What are like some example, like this has obviously become more relevant recently because of GPT, frankly, and how we had this rather big leap from like 3.5 to 4 even, where people were just seeing like, wow, this works way better. It can do way more. It's performing much better on all of these kind of benchmark metrics or even human level intelligence metrics. So what are some of the examples of emergent abilities of AI that are kind of causing this to float up to the kind of top of the public consciousness almost even?
Well, I gave a few examples, but I think just looking at the data, so GPT-4 was out, and I don't know if you used it when it came out, or even GPT-3 it was GPT-3. When it came out, it was really impressive, and I was blown away. I've been doing this for like 20 years. I was really blown away by it, but it wasn't, like, it was popular, and it was popular from anything I've seen before, but it wasn't as popular as it is in this moment. And so what changed that was Chat-GPT. And so what it made me realize is this AI is an alien intelligence, and we could have alien intelligence all around us. But what matters is kind of the communication bandwidth to that alien intelligence. And so while GPT-3 was sitting there, just as intelligent as now with Chat-GPT, but it couldn't communicate itself well to humans. It was an alien, right? How could we expect it to communicate with us? And so it was kind of unwieldy, very difficult to use. You could get it to do it because it was intelligent. But when ChatGPT came out and you could talk to it like you and I are talking, or you talk to it as if you're asking someone to do a task for you, I think it just blew people's minds and captured their attention. And it was really this reinforcement learning with human feedback to teach it what humans are, how humans like to speak, what humans expect. And we needed a human to teach the alien to how to work with us. And so I think that's the important piece here, was that, like, and it makes me think of people with autism, or even Stephen Hawking. Imagine Stephen Hawking didn't have a keyboard or paper to write with. Like, one of the most intelligent humans to ever walk the earth, he wouldn't be, like, we wouldn't even know, right? He wouldn't tell us about Hawking radiation in black holes. And so I think this communication bandwidth is a really important concept.
Definitely. And there are like a lot of assumptions, I guess, in the animal kingdom about, like, we assume dolphins are super intelligent and elephants, but like our ability to communicate with them and measure it is limited by the fact that we, speak English and we observe things with certain sensory organs, and we can't fully understand what's going on inside of their minds and how they process information. Maybe one day we'll find out, like, these dolphins are really smart. They're super intelligent. We just didn't have the tools.
Exactly. And they don't have opposable thumbs, so they couldn't necessarily build tools as well as us. And I often think that, like, why not? If you look at their brain, they have the potential to be intelligent, maybe not as much as, or maybe they're more intelligent because they have even bigger brains. But it's like, let's just assume they were super intelligent. What would they do? Like, they'd probably, like, stay out of our way because we'll, like, stab them with a spear or something. And maybe they're just, like, super happy. And I've swam with dolphins, and they go up to you and they look in your eyes and they play with you, and, like, I don't know, it makes me, as I interact more with this new alien species we call AI, it makes me think that there's more non-traditional forms of intelligence that we just don't communicate with, like, even in our body. Like, imagine how much intelligence, imagine if you had a connection to, I don't know, your pancreas, and you saw how intelligent it was, like, changing the homeostasis set point of your blood sugar levels in your body. There may be an intelligence, or maybe, like, even the universe somehow, or maybe this is what people call God. There's this, like, universal intelligence, or maybe there's even an intelligence intelligence of society that's even hard to communicate with because it's a non-traditional form of intelligence. And I think somehow we're only set up to think about, to understand, to even call intelligent things that we can communicate with and are similar to human intelligence. And maybe if there's a way we can have a translator, we can tap into many different massive forms of other intelligence that we haven't tapped into yet.
Yeah, and it can kind of augment your own intelligence and the way you think. Like, I mean, for instance, with the dolphin, it lacks the opposable thumbs and other ways that we interact with the world that maybe limited the ability of its potential intelligence to achieve similar things. And then also, like in the example of, you know, if you were in touch with your pancreas in this way that you described, it could alter your understanding of the importance of eating healthy food or lifestyle choices like exercise, because you wouldn't just have this kind of, oh, it feels good, I feel better over time if I do it. You would maybe have this very keen understanding of like, I actually know what it's doing to me on this crazy, sophisticated level.
Yeah, it's a good point. And Steve Jobs, I don't know, I saw some video where he called computers the bicycle for the mind. I think AI is like the rocket ship for the mind, or maybe even it's like the mind for the mind, or it is the mind. No, I agree. I think AI has a potential to make us healthier, even to make us more empathetic. Like, let's say you had autism or whatever, and you were wearing these glasses, and it was like, oh, when you said that, it made Chris sad. And then you're like, huh, interesting. Like, I think it can make us more human than we've ever been in our entire life.
Help us understand and perceive our limitations and perhaps respond to those limitations differently. Yeah, that's really interesting. I mean, on that notion of potential, and we've kind of discussed, in your view, this limitless potential in some respect, how does that complicate efforts? Like, I know this week the Biden administration sort of started proposing some AI regulations, but given this potential that's a rather massive unknown, how does that complicate these efforts and like our ability to, you know, we've talked about alignment, like align it with our goals or regulate it from a government that often already struggles to keep up with technology. What do you think about that?
Yeah, I think I have a lot of family in government, and I see a lot of what happens behind the scenes, and it's a really difficult problem. I think the government gets a lot of hate. I think they're trying to do their best. I don't think what worked in the past of, like, let's say we were all growing corn and we wanted to regulate like not using certain pesticides or whatever, and you know, there's lobby, like that works because things were slow, the government's slow. I think it was fine. Like the government just needed to change a few things every 10 years or 100 years. But I don't think it's going to work in this world unless something changes. And I'm optimistic we can all work together to find a solution, but it does worry me because at some point we may need regulations. So where are the regulations going to come from? Maybe it's a few good people who come up with a product. Like I'm generally a believer of laissez-faire economics, of the free market can solve things. So I believe someone will come up with a product to protect you and say, hey, buy my AI protector that protects you against deep fakes, that protects you against. And I think that may be the way it does it. And as strong of a libertarian I am and a believer in laissez-faire economics, there are some problems that just free market capitalism can't solve. For example, with nature, with people who, let's say, have mental disabilities, can't think for themselves, or very, very poor people. So there needs to be, I would say, I've always estimated that 5%. Like, I think 5% of GDP should go to the government to protect nature, to protect people who can't necessarily help themselves. And so I think I have a similar view of AI. Like, I think most will come from the free market because people will want to protect themselves. Like, you buy cars with airbags. I don't know if there's a government regulation, but my guess is even if there wasn't a government regulation, people want to be safe and companies would still have airbags in there. But there's still like these 5% of things where there's this like corporation dumping stuff into the river that I think is really hard for pure free market to solve. And so I think the government will need to jump in on a 5%, but I don't think it's going to solve the 95% of what we need to solve. I think that'll come from the free market.
I think we covered it. It was good, man. It was a good chat.
Cool. All right, Chris. Well, thanks for organizing these questions, and I find them really interesting. And have a good day.
You too, Brad. See ya.
All right.